Welcome to another Macrone Group webinar. My name is Charles Zona, and today our presenter is Dalia Yablon. Before we get started, I would like to give you a bit of Dalia's background. Dalia is the founder of Surface Car, an AFM consulting firm located in the Boston area. Surface Car specializes in surface and interface characterization, measurement, along with education and training, focusing on scanning probe microscopy. Prior to Surface Car, Dalia spent a good portion of her career at ExxonMobil Research and Engineering, working with the Chemicals Division to develop new AFM-based imaging methods. Dalia is also the editor of the book Scanning Probe Microscopy in Industrial Applications, published in 2013 by Wiley Publishing. Dalia will field questions from the audience immediately following today's presentation, and this webinar is being recorded and will be available on the Macrone Group website under the Webinars tab. And now I will hand the program over to Dalia.
Good afternoon, everyone, and thanks for being with us today. Today I'm going to provide a brief overview of some of the surface properties and measurements of materials that AFM can measure besides topography, which is probably what it's best known for. So on this next slide, I have some images that I pulled off of some vendor websites of some of the really beautiful nanoscale topography images that AFM can generate. Now, as we had discussed in the webinar earlier this year, AFM does provide true Z information, unlike its counterparts in electron microscopy. And so you can get a real map of your surface. So here I've pulled off some images of some very thin nanosheets of pyrene. Here are some biological examples. AFM is used a lot to image biological samples. So this is a live E. coli cell, which was imaged in situ. This is a human lung cell. Here are a couple of very pretty high-resolution images of gold nanoparticles up top. This is only a 450 nanometer scan. And then aluminum. This is a 500 nanometer scan on the edge. And here is a really pretty topography of butterfly wings. Very interesting morphology that they have. And all of this imaging can be done with very high resolution. So about 5 nanometer resolution in X and Y, angstrom resolution in Z, and a flexible environment. You can image either in fluid, vacuum, or air. That's the power of AFM. And then one more word on topography. Probably one of the most common applications of using AFM for topography is in the semiconductor industry, where it's used for quality control to measure the critical dimensions of features that are important in that industry. So here, for example, these trenches, they want to know very accurately how deep are they, how wide are they, how rough is the bottom of the trench and the sidewall of the trench, and you can see here how that can be very easily visualized and measured quantitatively with AFM. And here is another feature. Again, we would want to measure the height, the roughness along the sidewall, which all can be done with AFM. But AFM can do a lot more than just topography, and that's really the focus of this webinar this afternoon. So briefly, I just want to review the principles of operation of AFM so that we're all on the same wavelength. We have a very small cantilever with a sharp tip hanging off the end. This cantilever has the dimensions approximately of a human hair, and this tip cantilever assembly is typically made of silicon or silicon nitride. So this is an SEM image of the cantilever, and it's placed right here. And then we have a laser that's reflected off the back end of the cantilever and then directed towards a position-sensitive detector, which can monitor the up, down, or side-to-side motion of the cantilever as it interacts with the sample. And then in this configuration of the instrument, we have a piezo that's positioned underneath the sample that's going to move the sample around in X and Y, and the cantilever will interact in a variety of ways as the sample is scanned, and then we track the motion of the lever with this laser or optical beam. So that's the general principle of operation. And to first order, you can use that to map the topography as we've discussed. However, AFM, the power of it, besides its flexible environment that you can operate it in, like fluids, its other power really resides in being able to map all these different properties of the surface simultaneously with the topography. So for example, there are a whole slew of techniques, and I like to think of AFM as an umbrella, and then there are a whole slew of properties and techniques within each property that can map it. So for example, to map mechanical properties, I've just done a partial list here. I have about 8 different modes that can map different aspects of mechanical properties of your surface. Same thing with electrical properties. Here I've only listed 5, again an incomplete list of different modes to map different kinds of electrical properties and interactions between the probe and the sample. Same with magnetic properties. We can probe the magnetic properties of your sample simultaneous with the topography. A growing field is probing the optical properties. So things like the Raman and IR spectra you can now start collecting with very high resolution simultaneous with the topography. And then you can use your AFM tip as a finger, high resolution finger, to do other kinds of experiments, not necessarily mapping properties of your surface, but perhaps pulling on molecules. The bio community likes to do this. They pull on proteins to unfold them. Lithography and manipulation to write very small size features. I'm sure you've all seen some school or university logos written with the AFM tip on high resolution. Manipulation to move molecules around. Even 3D nanoprinting starting to come in with AFM. But again, not just topography, all these different properties of our surface we can measure simultaneous with the topography. And I'm just going to give a very brief overview of some mechanical properties we can measure, some of these electrical properties, magnetic, and I'll end with some IR measurements that we can make now with AFM on high resolution. Okay, so let's start with mechanical properties. And so here I have an image where I've collected the topography and then what's called the phase channel of a tire tread sample. This is a 10 micron by 5 micron image. The phase channel gives you contrast collectively based on a bunch of material properties such as adhesion, stiffness or modulus, dissipation, and viscoelasticity. And so you can see in the topography channel, what we have here are a lot of these little carbon black particles from our tire tread material. And then in this phase or material property channel, we see actually a very different kind of contrast. I see regions that are bright yellow or orange, dark purple. These dark purple regions are in fact the little yellow dots that represent the carbon black particles. And then even these bright white areas. So that we can see this phase or material contrast channel is giving us very different contrast mechanism than the topography. We can see probably 4 or 5 different regions here corresponding to 4 or 5 different materials in the tire tread. And then what I can do is I can overlay or paint the phase channel onto the topography channel, which I've done here, so that now the color is actually corresponding to the phase or material contrast, and we can correlate this contrast from the material property with the 3-dimensional topography that we map simultaneously. Now what I just showed was an imaging measurement that AFM can do based on mechanical properties, but it can also do single point measurements to get more quantitative measurements now of important properties such as stiffness or modulus and adhesion. Those single point measurements are shown in the schematic before, where you literally at a single point just poke the surface with your cantilever, and you measure what's called these force versus distance curves at these individual points on your sample, where the force is typically in units of nanonewtons and the distance is typically in units of nanometers, so tens, hundreds of nanometers, maybe even up to a micron. And you follow the poke in as my cursor is going, and then as you retract, you can see that the approach, and the retract actually do not track each other completely. And so we can get from this section of the curve information on modulus, and from this depth of what's called the pull-off when we try and retract, that gives us the adhesion information. And so we can do that at single point measurements. But we can also map that across a whole area, just create a map of these single point force curve measurements, and we can create maps of adhesion and the elastic modulus. And this is an example of this measurement done on epithelial cells. We can even build a histogram on this sample to really get some statistics and a quantitative value of what the adhesion is. Notice in the units of nanonewtons, and the modulus. The cells are quite soft, so this is kilopascals. And we can see here this was a modulus in this histogram of moduli. This is a modulus of the cells, and this is a modulus of the background, and thus get fairly quantitative measurements on these important mechanical properties of our sample, in addition to being able to image and get mechanical contrast based on our from our sample, as I showed in the previous example on the tire tread. Let's move on to a brief overview of some of the more popular electrical modes that AFM operates in. Again, the idea here is to provide our usual nanoscale topography, but now also we have access to channels that provide contrast based on electrical properties. These modes require an electrically conductive tip, which are commercially available and marginally more expensive than conventional silicon cantilevers. Often these modes also require the ability to image your sample in two passes, one to collect the topography and a second one at a slight elevation of a few tens of nanometers above the sample to probe the electrostatic or magnetic interaction. We'll start with Kelvin probe force microscopy, or KPFM, and then I'll review conductive AFM, electrostatic force microscopy, and magnetic force microscopy. KPFM maps the variation in contact potential between the tip and sample, which can be converted to the work function difference between the probe and sample. It is also referred to as surface potential or work function imaging. Applications of this method are diverse and include corrosion studies, photovoltaic effects in solar cells, and catalytic activity. It is another example of this mode that gives us sensitivity or contrast based on the electrical properties of the sample. In this case, its work function. Here is an example of a KPFM image. The KPFM signal has been overlaid or painted onto the topography, so we can see the 3D topography here, and the coloring is actually from the KPFM signal. This is a copper foil substrate that had flakes of both boron nitride and graphene. These flakes are only 1 atom thick, and so they were impossible to resolve in the topography channel alone. But by looking at the KPFM signal, we can see that the graphene flake has a different orange contrast compared to the bright white contrast of the boron nitride flake. And so mapping this tip sample potential easily differentiates these two materials. You can also obtain a localized map of conductivity of your sample. In conductive AFM, the conductive tip is scanned in contact with the surface, while a voltage is applied between the tip and sample. This will generate an image of the current between the tip and sample. The example here shows a topography and current image of a lithium-ion battery cathode, which is a composite with multiple materials. Its different components can be assigned thanks to this mode. In the current image on the right, we see two contrasts, purple and pink contrast. Down here, this current image is overlaid onto the topography, so we have a full visualization of the sample. In the current image, the less conductive purple regions are the lithium cathode material not covered with a polymer binder and conductive additive. The more conductive region in the pink area are areas where the lithium cathode material was covered with this particular binder and conductive additive. The final electrical method I will survey is electrostatic force microscopy, or EFM. This method maps the effect of long-range electrostatic force gradients on an oscillating cantilever and is useful for applications such as electrical failure analysis, measuring charge distribution, and detection of trapped charge. It's convenient primarily to image qualitative electrical properties, as the electrostatic force is measured between a biased cantilever and the surface as the lever is lifted a prescribed amount over the surface. This is that two-pass mode that I had mentioned in the beginning. Here's an example of amorphous bits on a DVD-RW. This is a topography image, and the EFM image on the right clearly exposes the amorphous bits formed, which are not seen at all in the topography image. A magnetic analog to EFM to probe magnetic properties is known as magnetic force microscopy, or MFM. Cantilevers with a magnetic coating can be used for this mode. In this mode, like in EFM, a cantilever is lifted over the sample, and the tip-sample magnetic interactions are detected and used to reconstruct the magnetic structure of the sample. In this particular application, a patterned array of magnetic cobalt structures was fabricated and imaged. The topography here on the left shows an array of submicron square dot structures, whereas the MFM image shows magnetic contrast and a very different type of structure associated with its magnetic charges that is obviously unique to the MFM contrast channels. These are some of the more popular electrical and magnetic modes available with AFM. This was just meant to provide an overview of some of the more popular ones, but there are certainly many other modes that focus on other properties such as scanning capacitance microscopy and piezo force microscopy to probe some of these different properties of a sample that might be relevant for a given application. So we've gone through how AFM can measure some mechanical, electrical, and magnetic properties. And now I want to review an area that has gotten a lot of attention over the past few years, which is combining optical or spectroscopic information with AFM and through the AFM platform. And the key information that this is adding, especially through these spectroscopic modes, is the ability to add now chemical information to the AFM topography. And the primary ways this is being done is by combining AFM and Raman and AFM and IR. AFM and Raman, the most popular way that that's being done right now, is doing these what are termed co-localized measurements of AFM and confocal Raman on the same area. And then for higher resolution, there's a technique called tip-enhanced Raman spectroscopy that's available. In order to combine AFM and infrared spectroscopy, there are also two main methods out there. One is an apertular scattering method, which a diagram or schematic is shown here, where you use the AFM tip as a very sharp antenna to really focus the IR light right underneath the probe. And then another method that's a photothermal method that relies on some mechanical motion of the lever in response to some heating by the IR laser. But I want to show you some applications of this. So we'll start with AFM Raman, and I'm going to focus on co-localized AFM and Raman. And so here's an example of this being used to study graphene, obviously a very popular choice for Raman. So here we had a graphene flake, and this was the AFM topography that we all know and love on the nanoscale, very high resolution. But turns out in this flake there was some single layer, 2-layer, and 3 layers of graphene that the Raman signal is particularly suited to resolve, because each of these different layers, however many layers of graphene you have different signatures or peak in your Raman spectrum. And so correlating with this topography image, they were able to collect Raman signals of just focusing in on the peaks of the different single, here, double, and 3 layers of graphene, and could really then put a composite together and map out with this topography where these different graphene thicknesses were really mapped out in this flake, which you would never be able to do from just the topography alone. And then putting all the kinds of data together that we've reviewed, what they did is they actually collected here the topography and the chemical or the Raman image that we just discussed. But then going back to earlier parts of the webinar, they collected the phase image, which is giving us contrast based on the mechanical properties so that we can see that this flake is certainly differentiated from its background in terms of the mechanical properties. Not a whole lot of differentiation between the different flakes, though, in the phase. And then a KPFM image to map the contact potential difference and electrical property. And here we can certainly differentiate the triple, double, and single layer flakes, also revealing differences in these electrical properties as captured by this channel, in addition to the chemical information that we've unambiguously assigned these flakes, and all based on the topography channel. So you can see here a really nice example of mapping all these different properties on this sample. Really provides the most complete visualization and understanding of what's going on with the different flakes and their electrical behavior. And again, a very rich overview and understanding of this sample far beyond just what the topography alone offers. Now, before we go into some of the AFM-IR examples, I just wanted to say a few words about resolution and this optical information. So typically, optical spectroscopy measurements such as Raman and IR are limited by the diffraction limit, which is lambda over 2, where lambda is the wavelength of the incident light. For the IR, which typically has very long wavelengths associated with it, that meant the resolution was limited to microns. So to be able to put this onto an AFM platform and achieve resolution of less than 100 nanometers very easily, and in some cases even less than 20 nanometers, is very impressive. And we can still combine this chemical information from the IR with the topography from the AFM, and then other channels that we've already explored today, such as mechanical properties. So here's an example of using AFM-IR to image bacteria. So here is a topography image of the bacteria. And then the IR image was zeroed in at particular peak, 1650 wave numbers, which corresponds to a protein, and then 1740 wave numbers, which corresponds to the triglyceride. And you could easily map the distribution of these two components in this bacteria and see where these individual components are with very high resolution. Another example for polymer material application is AFM-IR image of a dye block thin film. So this dye block was PMMA and polystyrene. We can see the topography image here. And then the IR absorption image at 1730 wave numbers, where you can now easily distinguish these two components, where one's absorbing a lot and the other not so much at this peak, which would enable unambiguous identification of which component is PMMA and which one's polystyrene. And then here, even higher resolution. So here, this length here is only 200 nanometers. Here it's 100 nanometers. And you can see here they tuned off of the absorption peak and see very little contrast, showing that this is real, this contrast seen at 1730 wave numbers. So having this AFM platform to make these IR measurements and to build this IR information on top, on a very high resolution, less than 100 nanometers, on top of the nanoscale topography and mechanical property information from the AFM, again results in a very powerful tool to provide a very complete characterization from many different angles of the sample. Okay, so in summary, I hope I've been able to convince you that AFM provides information on more than just topography. I showed you a lot of applications that show the different surface properties that AFM can probe. So we started with mechanical, showing that AFM can provide very effective maps of different properties like adhesion and stiffness. It can also provide maps on viscoelasticity and friction. Did not show you those particular applications, but still possible. We talked about electrical modes and talked about modes that AFM can map the surface potential or work function, electrostatic interactions, and current. It can also image other properties such as capacitance and piezo forces. Again, these two I did not include. We talked about recent advances in coupling chemical information like Raman and IR to AFM topography, and then also magnetic interactions using magnetic force microscopy. So we can map all these different properties in addition to topography, all on the nanoscale, with a less than 10 nanometer lateral resolution and sub-nanometer resolution in Z. One caveat on this resolution is the IR information is not quite at that level, but it's close. And not to forget that AFM can do this all in a flexible environment in either fluid, air, or vacuum, resulting in a really powerful characterization and visualization tool that can provide you so much information on your material and on your surface in terms of all these different properties in conjunction with topography, all on the nanoscale. So hopefully this has been useful to you guys and maybe whets the appetite to try or learn more about atomic force microscopy.
Okay, thanks, Dahlia. We're going to take questions now. If you go ahead and just type in your questions in the question box, Dahlia will start fielding those questions. And Dahlia's contact information is up there on the right. And she can also, we're doing a course with Dahlia, November 6th through the 8th. If you're interested in that, please visit our website for more information on that. And Dahlia, I'll hand things over to you. Can you see the question box over there?
Yeah. Chuck, you can hear me okay?
Yes, I can hear you fine.
Great. Okay, so I see a couple of questions have come in, so let me start addressing them. The first question is what are the constraints on a sample that you can measure with AFM? Excellent question. So there are basically two main constraints. The first one, it has to fit into the instrument. Not a surprise, it's a microscope. AFMs actually come in two types, a small sample instrument, which maximizes on the signal to noise, and a large sample instrument to accommodate large samples. So I would say as long as your sample can fit into the instrument, you should be okay. And if you have a challenging geometry or a large sample, you might have to go to a large sample AFM. I can tell you that when I was at ExxonMobil, some of the most exciting samples I personally worked on were engine parts that we would look at. So as long as it fits, you can image it. And the other constraint is flatness, and that's constrained by the Z piezo in the AFM. So basically, over about 100 micron area, depending on which instrument you use, you can't have more of a Z range than 5 to 15 microns. That means not only a range, but even features. So if you have features that are much higher or deeper than that, the AFM will struggle, and you may lose signal when you try to image that. So again, it's flatness and constraints on the sample. in terms of fitting in. Okay, a second question has come in. That was about the course. Do you need to be an AFM user to attend the course? And the answer is no, you do not. The course is actually designed for, I would say, either people who've never used an AFM or very early users. It's really, the purpose is to provide an overview of the AFM and get people exposed to the technology and seeing what the capabilities are, understanding the capabilities and its limitations. Okay, a third question. How is the measurement affected if I need to use a heating stage? So heating stages are certainly available on AFMs. They are, the commercial heating stages typically go up to several hundred degrees C. And what is so you can certainly do it. It's a pretty common application. The things you might have to worry about if you're doing measurements at an elevated temperature, for example, are you may have to be a little patient. You heat up your sample and then you need to give it some time to thermally equilibrate at that temperature until you can make your measurement. So because we're imaging at the nanoscale, we are very sensitive to drift and other motion. So as long as you're patient and you're willing to let your sample and system equilibrate at the higher temperatures, you should be all set. Not a problem, and like I said, pretty common application to do all the kinds of AFM measurements I've described at temperature. Let me see. I think that pretty. Let's see. Okay, one final one that comes in, and maybe this will be the final question. Is there any literature on how to pick the correct cantilever, i.e. for different samples? So that is one of the $64,000 questions when you do AFM. So you really have to, I would say, understand the tip sample physics and interactions in order to be able to properly select your cantilever for the measurement. There are certainly some guidelines, some formulas that we all base it on, but if you really understand what the nature of the interaction between your tip and sample is, that's the best way to pick the cantilever. The cantilever matters a lot. The spring constant, its material, the shape of the tip, and it's really important. It's probably the most important parameter you pick when you run your AFM. Just to put a plug for the course, we go over that in a lot of detail in the course because, like I said, it's a very important parameter for AFM operation. One of the most important ones, and I would also say one of the most poorly understood ones, is probably one of the factors that most of my students least understand, at least coming into the courses. Okay. All right, maybe we can do one or two. We have time, Chuck, for one or two?
Yeah, sure. If I see there's a couple more rolling in, if you want to address those. And we will have, if we don't get to a question, we have your contact information and the question that was asked, so Dahlia can follow up with you if we run out of time here. So yeah, go ahead, Dahlia. If you want to take a few more, that'd be great.
Okay, sure. These are really good questions coming in. All right. Someone asked to give a general idea, I guess, of the kinds of thermal measurements possible. So the general idea of these so there are two kinds of thermal measurements. One is that you actually heat your sample. And so you're measuring the morphology or the topography or the mechanical properties, that's a common one, as a function of heating. For example, you can look at melting or crystallization processes in situ as you heat or cool your sample, and then you image, again, in situ, actual processes that are a function of temperature. So in the polymer community, this is done a lot. I also, for example, have done a lot of measurements, again, in the polymer world, where mechanical properties are a function of temperature. So it's interesting to measure these mechanical properties directly at temperature and see if you can capture the differences. So hopefully that answers that question. Okay, one question is on a pretty common technique called peak force Q&M. This is a force curve based method to measure nanomechanical properties of polymer blends and composites, and asking about the accuracy of the modulus measurements on this mode of operation. And this is a technique that is commercialized by Bruker. So I would say it's a very useful technique. I myself use it a lot. In order to get quantitative measurements of modulus, you have to work really, really hard. It is not an easy measurement to get quantitatively accurate. You need to work hard on the calibrations. You need to have a really good understanding of your tip sample dynamics and your indentation depth to make sure you are working within the range that this measurement is accurate. And I would say even then, you know, maybe within 10% after you've worked really, really hard and spend a lot of time on your sample. I would always, you know, I'd like to always joke that, you know, it was a good method for, you know, people who really had the time in the lab to focus on it. If you're trying to do quick and dirty measurements, I would say much less confident of the modulus measurement. What it is useful for is it's great also for just screening samples. It's a very easy mode to work in, and just to get some kind of baseline contrast and topography image, it's great. Okay. So another question, if the minimum resolution is 5 nanometers, can you still get topography at the slower resolution limit? So resolution is always kind of a tricky subject, I would say, for most microscopists. The reason I say 5 nanometers is that is really for commercial instruments with commercial levers not operating in some super duper fancy modes. Now, if you want to operate in a more sophisticated mode and you have, you know, a real first class research instrument, you can certainly get topography below that. So in air, AFM now, you know, research level instruments under certain conditions and with maybe more sophisticated modes can get atomic scale resolution. And I would say, you know, that's really been around probably the past 5 to 8 years. It's not, it will be sample dependent. If you can immerse your sample in a liquid, that's something that really helps get at that higher resolution. So I would not, you know, I don't push the atomic scale resolution because it's not something that's really applicable to kind of any sample that you throw in under your system. It'll also be well prepared. But in terms of this question of the limit of topography, I would say on these research level commercial instruments, it is atomic scale. Again, provided that, you know, your sample cooperates and you're willing to operate in a more sophisticated mode. Okay. Maybe one final question, on the thermal one. How can we isolate our sample from the substrate with the thermal measurement? And is it possible to do with room temperature? So if you're heating, so it depends on what direction you're heating from, right? If you're heating from the bottom, which is what all the heating stages are, then it's going to be very difficult to isolate your sample from the substrate. However, you can use heated probes, which is another kind of thermal measurement I did not mention. So you can have these probes that you heat them, and then you have localized heating just at the probe, at the point of the probe. That is useful for measuring thermal transitions like TG or glass transition or melting types of transitions right at the point below your probe. And that is heating from the sample, not from the substrate. So that would be a better approach to separate your sample from the substrate. But again, you need to have access to these heated probes, and the kind of measurement that you want to make is really a localized heating measurement. If you want to be imaging at temperature, it's a little more tricky to do it with heated probes. Okay, I think I've answered.
I think that covers a lot of ground, Dahlia. You've answered quite a few questions. And again, if there was one we didn't get, we'll get back to you on that shortly. I'd just like to thank everyone for attending today's webinar, and thank you, Dahlia, for lots and lots of interesting information to think about. And thanks again.